Hi, this is Professor Fernandez, and this is video 1 in lesson 27. We'll be talking here about integrals of transcendental functions. So as you see on the screen, there's exponentials. Some of these will generate logarithms, and then there's also trig functions here. So these examples come from Calculus Simplified, so let's just dive into these 4. There are other things down here in the screen where you see a bunch of theorems, and these are just integration results that we will use throughout the calculation of these examples. One thing to mention real quick is that if you'd like a review of the integration concepts that we're using in this video, check out videos 18.1 through 18.3. We'll be using things, for example, up here, like the evaluation theorem when calculating a definite integral, but also properties of integrals like the integral of a sum is the sum of the integrals, for example. So check out those videos for a review of that. Okay, let's go over here to the left-hand side and take a look at the first example. So let's see what this says. I'll zoom in a little bit here. Calculate the integral of 3 times e to the x. The first thing to do to make it a little simpler is to say this is equal to 3 times the integral of e to the x dx. That's, again, one of the properties of integration. You can pull out these multiplicative factors outside the integral. Okay, so now integrating e to the x dx. I'm going to scroll down here. This is one of those fundamental integrals. I'll zoom in here so you can see it clearer. The integral of e to the x is e to the x, because you might remember that the derivative of e to the x is e to the x. And then, again, thinking back to what this symbol means, it's really shorthand for anti-differentiation. So if the derivative of e to the x is e to the x, then this tells us that the integral over here of e to the x is the thing that we differentiated. And then with the plus c because it's indefinite. Okay, so that was pretty easy. So I just have 3 times e to the x plus c. There we go. That is my answer. So let's check out the second one. This one is a sum of 2 functions. So based on our integration properties, we can split this up into the sum of these 2 integrals. One of these is using the integral version of the power rule. So that, again, goes back to some of the videos in lesson 18. We add 1 and divide by the results. Add 1 to the exponent, divide by the result. And then over here, we're integrating an exponential function that is not e to the x, right? So the integral is only slightly more complicated. I'll scroll down here. There is the rule down there. Zoom in a little bit. So if I integrate an exponential function in general, not just e to the x like we did over here, the answer is the exponential function divided by the natural log of the base. This goes back again to the fact that the derivative of an exponential function is write it over, multiply by the natural log of the base. So therefore, the derivative of 1 over the natural log of the base times b to the x is b to the x. So again, going backwards, then the integral of b to the x dx equals this thing. And that gives us that rule down there. Okay, so to apply that up here, integrating 2 to the x would be 2 to the x divided by natural log of 2, and then we have our plus c, and that is our answer. Great, so we're doing these pretty speedily because I'm starting simple here. So now let's calculate this one that we see, x squared plus 1 divided by 2x. First thing we can do is simplify this. So x squared plus 1 over 2x, I'm going to divide in the 2x into each of the terms in the numerator. So in the first part, I get x over 2. And I can cancel out a factor of x here because the original function is not defined at 0. So I don't have to worry about whether x is 0. It already can't be 0 from the initial presentation of the function. So I get x over 2. And then plus 1 over 2x. So the integral dx of this original function is the same as, let's move things around here a little bit, is the same as integral of x over 2 dx plus the integral of 1 over 2x dx. So the first of these, this one, is a integral that we can do without any of these fancy rules down here. So we can, if we'd like, we can pull out the 1/2 and integrate x dx. That integrates to add 1 to the exponent, so x squared divided by the result over 2. And then we still have to do the integral here of 1 over 2x. We can pull out the 1/2 also, integrate 1 over x dx. And then here is where we are going to use a new rule, at least new to this video, new to us. So now I'm going to integrate 1 over x. You might remember from the integral version of the power rule, integral of x to the n dx, was x to the n plus 1 over n plus 1 plus c, so long as n was not equal to -1. And you can see why, right? If we're going to divide by n plus 1, if n equals -1, we're dividing by 0. So can't do that. So therefore, this restriction was always there for the integral version of the power rule. So finally, we are now going to discover, if you will, what happens when you integrate 1 over x. In other words, the n equals -1 case over here. And the answer is this theorem 5.8. So when you integrate 1 over x, you get ln of absolute value of x. All sorts of interesting reasons for this. Some of them are discussed in the book. For the purposes of this video, I'm just going to use this fact and plop it in over here so that the 1/2 times the antiderivative of 1 over x, right, is ln of absolute value of x. And then I will clump my plus c's from this indefinite integral and that one into some plus c. It's an arbitrary constant anyway, so we don't need 2 of them. And this is my final answer. So 1/2 x squared over 2 plus 1/2 ln absolute value of x. Okay, so that is it for those first 3 examples here. And you can see again that by design, these were kind of meant to increase subtly in difficulty, right? This one was just straight up e to the x times 3. Here we were adding 2 and then different integration rules, if you will, that we needed to use for each of these. And then here there was a little simplification step using the algebra to divide these out first and then split them up. So let's look at 5.19. So the difficulty added here is really just that, number 1, we're dealing with trig functions, and number 2, we are now doing a definite integral. Okay, so first thing I'm going to do is I'm going to split this up into the integral of sine evaluated from 0 to pi, plus the integral of cosine, also evaluated from 0 to pi. Okay, so now let's talk a little bit about the integrals of sine and cosine. So that's this these last results over here. Really, it's the ones that I put down here. I wanted to add all of the information for the reciprocal trig functions because that's always nice to have. But for the purposes of this example, we're just going to use what's down here. So sine and cosine, right? The integral of cosine is sine because, again, the derivative of sine is cosine. The integral of sine is negative cosine because the derivative of cosine is negative sine. And really, these are the only 2 that we need for this example. So I'm going to use that. Okay, so integral of cosine is sine. So let's go back up here, and we see an integral of cosine right there. So that's going to be sine x evaluated from 0 to pi. And then we have cosine, we're integrating sine here left, so we're going to scroll down. If I integrate sine, I get negative cosine. So this is minus cosine of x evaluated from 0 to pi. Okay, so then we just do the fundamental theorem of calculus step. So this is going to be minus cosine pi minus cosine of 0. You can see that I kept the negative sign outside. You could, if you wanted to, bring it inside and write this as negative cosine minus negative cosine of 0. Right, that's okay. I won't do that just because it's easier to just keep the multiplicative factors, whatever they are, positive numbers, -1, whatever, on the outside. Okay, and then we were adding, so plus, and then the fundamental theorem step here, evaluation theorem step here, this is sine of pi minus sine of 0. Okay, great. And then now we just have to calculate this out. So at this point, the calculus is done, but we just have to do some evaluation of particular values of sine and cosine. So cosine of pi is -1, minus cosine of 0 is 1, plus, and then sine of pi and sine of 0 are both 0. So we get no contributions from here. Great, so we have equals minus -2, so 2, and that is our final answer. Great, so zooming back out here, quick things to mention at the end of the video. Like I said earlier, these were examples that were designed to increase in their difficulty in different ways. Probably the thing that I want to mention most, if I just erase everything so we have some more space here to see what's going on, is just zooming in over here. So at this point in the course, right, this is lesson 27. We've done a lot of calculusing, if that's a word. And we have learned that integration is much harder than differentiation because it's never quite clear what rule to apply, right? So if I zoom in here, I'm not quite sure if I'm going to have to use any fancy techniques. Admittedly, we haven't learned that many fancy techniques in this course. Integration techniques are normally par for the course for Calculus 2. That's one of the first things you study in that follow-up to this course. But that being said, like, how would you know, right? That's always a question with integration. How do I know, given a function that I want to integrate, what integration technique to do? And I wanted to discuss this example here because the answer, as with limits, as with anything else in calculus, is try to simplify the function first, right? So you may stare at this function for a while and not know how to integrate it, but once you do this, as we did, right, and simplify it to a function that looks like this, now it's a little bit clearer how to integrate it, right? This by itself, it doesn't seem like I know what to do with it, but this one, integral version of the power rule, and this one ends up generating a natural log. So that's really the best, most important takeaway that I have for you, right? The rest of these are all about knowing your integration rules for particular types of functions, sine, cosine, exponentials, and the natural exponential, e to the x, or exponentials in general. Great, thanks for watching.